Welcome back, everyone. It's my pleasure to introduce our final speaker for the conference, Anton, who will be talking about symplectic structure in Jackiw-Teitelboim geometry regarding gravity.
Well, gravity and geometry is the same, right? Einstein teaches us. Well, thanks a lot. Thank you very much to the organizers for an invitation and for an opportunity to speak here. Of course, given the last talk of the conference, that's a huge responsibility. Up to now, it was perfect. Well, now I don't know. I'll do my best. So I will be speaking about some instance of symplectic reduction in the infinite dimensional case in some particular field theory. This is a joint work with Anton and Renken, and I will start by reminding you some relatively standard stuff from finite dimensional equivariant symplectic geometry, and then we'll jump to that infinite dimensional example. So let me start with something that can be called two cycles and reduction. So is my writing possibly too small? Are you good? Okay, good. Perfect. So here is a context. Let's say G is a connected Lie group. This beautiful G is its Lie algebra. And let me take M, also a connected manifold, and let's say G M carries a G action, and let's say M is symplectic, so it has a symplectic form, and since it is symplectic, it also has a Poisson bracket on functions. And let's assume that the G action on M is Hamiltonian. This means that there is a map, mu, to the dual space of the Lie algebra. And there is an equation in which I never know what's the correct sign. So we consider fundamental vector fields corresponding to elements of the Lie algebra. So these are vector fields on the manifold. We substitute them into the symplectic form, and we want the corresponding one forms to be exact, and their primitives are pairings of the moment map with the corresponding element of the Lie algebra. So that's the moment map condition.
Sorry, what's GC? What's GC of MW, M omega?
Omega is a two-form.
No, what's GC? I think it's the action. It's an arrow. C is an arrow.
Oh, sorry.
Well, it's G and then circular arrow.
Oh, that's the action. Yeah, sorry. Yeah. But you're quite right. That's maybe a bit too fast. But okay, that's the standard setup in equivariant symplectic geometry. We have a Hamiltonian action of a Lie group on a manifold, and that's the main equation there. So now let me recall that in this case, we automatically have a two-part cycle on the Lie algebra G. So every time we have that, we automatically have a two-part cycle. And this two-part cycle is defined, or one way to define it is as follows. Let me take a function which is a pairing of mu with x. It's a function on M, and I take a Poisson bracket with a function mu y, and I subtract from it the function which corresponds to the Lie bracket of x and y. Sometimes in definition of Hamiltonian actions, we require this thing to be zero. But in general, it is not zero. But it's always a constant, right? A priori, how it's written here, it is a function on M, it's another function on M, but it turns out that that difference must be a constant locally, and since M is connected, it's a constant globally. So this thing is just a number. And this is clearly skew symmetric, and then it satisfies a more complicated equation, which says that this is a two-part cycle on the Lie algebra G with values in reals. So if you have that, you also automatically get the central extension of the Lie algebra G. So you define G hat to be a direct sum of G and a copy of R. It of course projects on G. So R embeds in it as a central line, and this guy C defines for you a Lie bracket on this direct sum. So the cocycle C may be trivial or non-trivial. Being trivial means that in the end, the Lie bracket here is just the Lie bracket on G plus the zero bracket on R, maybe up to some linear transformation. But it may also be non-trivial, in which case there is no isomorphism to G plus R. So in fact, you can now say, if you want, let's assume that this central extension of Lie algebras integrates to central extension of groups. It's not going to play an important role in the talk, but for simplicity, let's assume that. So you can actually think that this is a central extension which acts here. But the central line or circle acts trivially. So you reinterpret this action as an action of a central extension. And then you upgrade your map mu to the map mu hat, which goes to G hat, which is star, which is G star plus R star. R star is still R. And actually, this map mu hat, depending on whether the central extension was trivial or non-trivial, it looks as follows. So let me draw the picture in the following way. So this is G star, and this is this R direction. And this map mu hat lands either in the hyperplane which corresponds to the value 0 here, or if the central extension is non-trivial, it lands in some, maybe let me try to color it. So it lands in some non-trivial hyperplane, which may be a hyperplane of 1 on the R-axis. Actually, if it's non-zero, you can always choose your scale and decide what is called 1, right? The generator of R is traditionally called 1, and you can decide where that 1 on your line is.
So you're saying the R component is always trivial of the map. It's a constant map in the R.
Yeah, exactly. It's always like whatever you do, it's always sitting in some hyperplane. If the central extension is trivial, you're going to be basically back to what you had before. It will be lying on the floor here on the R equal to 0 point, or it's going to be sitting in some non-trivially distanced hyperplane from 0. But it's going to be always a constant.
Sorry, is G being a connected Lie group sufficient to make the pairing of the angle brackets non-degenerate?
But that's by definition, right? Because G star and G, by definition, right? The dual G star is dual of the vector space G. So that bracket is by definition the perfect pairing, right?
Should I assume that the field is like characteristic 0?
Sure. Yes. Oh, differential. Yeah, this differential geometry lives in characteristic 0. Yes. Like maybe one indication to that. Yeah. Okay. So that's one piece of standard vanilla that I wanted to remind you. And maybe the second piece is reduction. So suppose that in this context, we want to do reduction corresponding to an element, say, psi of G star. So we want to define a reduced space. Now, let me assume that the central extension may be trivial or non-trivial, but I will be assuming that there is a central extension. So then the recipe, how you do reduction at the level which is non-zero, or even at the zero level, if there is a central extension, is the following. It's called shifting trick. So this M psi is defined like this. So we consider pairs of a point on M and a point in some other space that I will now describe. So you consider points in the product M cross some quadjoint orbit. Now we'll say this is a quadjoint orbit of what? And these are points which satisfy now the condition that the sum of the moment map on M and the coordinate in that space is equal to 0. And now you divide it by the diagonal action of G. So this guy is a quadjoint orbit of G hat in general through the point minus psi, and here you should put your 1 or your 0, depending on whether the central extension was trivial and non-trivial, and we are choosing always that hyperplane to be living at 1, just to simplify our life. So then there is a binary choice here. Right, so so this space is automatically symplectic. And so then this is some kind of standard symplectic reduction that you find in symplectic geometry books. And then this space is also symplectic. And that's usually how in applications to physics we find so-called reduced phase spaces or spaces which correspond to phase spaces of dynamical systems or Hamiltonian systems with symmetry. So, right. So these are 2 points that I wanted to fix before diving maybe into a little bit more infinite dimensional story. And tell me whether you have some worries or questions at this point.
Maybe just the question is, I'm rather unfamiliar with these things. Why do you do this? Or what's the point of this M psi?
Oh, okay. So like the general story is as follows. It's assumed that even though it looks like a complicated construction, right? There are many pieces. There is an action, there is a two-form, there is a moment map, right? It's assumed that this space is sort of easy. Maybe it's a vector space with a linear action of your group, for instance, or something that you can manage rather easily. You know many things about that M. It's some kind of space where you have a very good control. So the whole strategy is based on that. And actually, that's going to be a little bit the case also in our infinite dimensional example. Maybe not entirely, but still sort of. So then out of this construction, you build many symplectic spaces, right? So you basically choose any psi and you build like the whole family of those symplectic spaces. Those are not necessarily easy. Maybe they're complicated and maybe even very complicated. And the usual game is that you want to study this situation. You want to study that space, maybe your vector space with an action, and derive properties of those spaces, whatever they are, symplectic volumes, cohomology rings, or whatever. Like you can ask various questions. to some questions you can typically give answers, especially, let's say, if the group is compact. And maybe the moment map is proper, then there is a whole very beautiful technology. That would be more like a topic of a mini course or maybe a course rather than a final talk of a conference. But that's some kind of standard game which is very, very productive. So now let me give you a motivation for this infinite dimensional story. This is so-called Jackiw-Teitelboim gravity, and I will also here describe our results. So Jackiw-Teitelboim gravity is a Lagrangian field theory, which is defined in the following way. So let's consider sigma. It will be an oriented surface, a two-dimensional surface with boundary. To simplify life, I will assume that the boundary has only one connected component. It's a circle, but in principle, you can consider more connected components. Let's say I will have a sort of ambiguity. In many cases, I will be saying that sigma is an open surface and sigma bar is a surface where the boundary is attached. You will see why I need a little bit make a distinction between those cases. Now, in a Lagrangian field theory, you need to have fields. And the fields in that theory are G, a Riemannian metric on sigma. And there is a scalar field, usually called dilaton. So this is a map from sigma to R. A Lagrangian field theory is supposed to have an action functional. And the action functional S of x phi is an integral over sigma. And here it's a rather simple functional. You take a product of phi times the curvature of your metric plus some constant. In this case, we choose that constant to be positive and integrate over the volume corresponding to the metric. And eventually, people add boundary terms at this boundary. I will not be describing you those boundary terms, but I will describe the influence of those boundary terms on what.
So what is x in that axiom?
Oh, sorry. Yeah.
Okay.
Good point. Yeah, I think probably there will be more and more things like that. Please do tell me. Right. So okay. So that's the functional. And of course, we know that the early Lagrange equations corresponding to that dilaton field phi, they tell you that Rg plus 2 must be 0. And this means that the solutions of early Lagrange equations correspond to those metrics being hyperbolic. So it's a nice geometric setup. And actually, what about the boundary terms? Of course, we will see that those boundary terms that I'm hiding from you, they are quite important. And in particular, so let me introduce a local coordinate system near the boundary. Let me say this is x and this is y. So x is a coordinate along the boundary and y is a boundary defining function. So, so the metrics that we are looking at are of the following type. So G explodes as 1 over y squared near the boundary. And here G naught is another metric which actually extends to the boundary. So you all know a standard example of such a metric, right? That's just a metric on the hyperbolic plane. Right? So we see that it explodes at 1 over y squared. if we take away y squared, then it would be just a Euclidean metric which extends to the boundary. Right. So that's the consequence of boundary terms. Now, this is one of the models of 2D gravity, right? Because gravity models, this means that you have a field theory of a metric. And in 2D, there is a variety of models. This is one model on the very wide market. It got a lot of attention long ago, maybe like 30 years ago. And now recently, there was again a huge peak of the physics interest, right? In physics, it goes periodically. And so there was recently another big interest in that model. And let me maybe cite at least one paper that we were reading and which was motivating for us. And what this paper is saying, it's saying many things, but one interpretation of part of these things, maybe like the beginning of the paper, of what it is saying, is as follows. So there is a symplectic structure on, let me put it this way, moduli of hyperbolic metrics. I will make it more precise in a moment. And there is a Hamiltonian action of Virasoro algebra. So that's what the paper, roughly speaking, that's part of what the paper is saying. And we got very interested in those statements. And what I tell you now is a sort of our take at it, like how to interpret or how to state or prove those things. You can call them, I don't know, statements or conjectures. I'm not quite sure, but so maybe now to state the results, I would need one definition. So we'll define the infinite dimensional Teichner space associated to that surface sigma. And Teichner spaces are studied in Riemannian geometry, and in complex analysis, it will be Riemannian geometry approach to it. So, so this will be the space of hyperbolic metrics on sigma. With this behavior, one over square behavior near the boundary. And we're going to divide it by the following space of diffeomorphisms of the closed surface. We take orientation preserving and connected component of it. And we ask it to be one at the boundary. So these are diffeomorphisms which don't move the boundary. Of course, those diffeomorphisms act on metrics. They preserve the hyperbolicity property, and they preserve this 1 over y squared property. So this is some infinite dimensional space. And maybe a small remark, right? Of course, all diffeomorphisms a priori act. Now we divide by the action of those things which preserve the boundary. So this means that the diffeomorphisms of the boundary going to act on the quotient space. In fact, that's not quite true. This is the universal cover of diffeomorphisms of the boundary, which will actually act. Okay. So now that's the main object that we want to work with. And here is a theorem, which I say again, this is sort of our interpretation of the physics story. I don't have a difficulty to say, does it exactly confirm what they're saying, or maybe not quite. So we say the following. Let's fix an invariant scalar product on the Lie algebra SL2R. Of course, all such scalar products are proportional to each other, right? So basically, that's choosing one point on a real line. So then there is a natural symplectic structure on this tight Miller space. So the action of if tilde if sigma bar is indeed Hamiltonian. And remember from the beginning of the talk, right? Once you have a Hamiltonian action, then there is a question, maybe you have a central extension, or maybe you don't have a central extension, right? So then this quadcycle C is non-trivial. And actually the second homology of that gadget, we know what it is. It's one-dimensional, and the corresponding central extension is famous, and it's called Virasoro, right? So that's why we have Virasoro. Maybe I want to add a couple of comments, and we're gonna get back to those comments in the end of the talk. Right, the word Virasoro, to many people probably in the audience, I don't know if you're familiar with that, right? One of the first associations is the word central charge, right? I think normally at this point you should ask me what is the central charge of that Virasoro. And fortunately or unfortunately, here the answer is a little bit like trivial. You know, right? We fix in the beginning that scalar product, and that scalar product determines for you what is the two form, and that two form tells you what is C. So basically, this central charge, the only non-trivial information is whether it's zero or non-zero.
So in particular, it does not depend on the manifold M on the surface, right? On the surface sigma.
It doesn't depend on the surface sigma, right? On the genus, right? Here we don't have all that much choice. It's just the genus of the surface. It does not depend on the genus of the surface. It only depends on what you loaded there as this scalar product. Right. Maybe I want to make some comments, because then I want to show you something about the proofs which have interesting elements. So they have their own value, but maybe before going into it, let's discuss a little bit what's going on. So first of all, as I say, the value of C is not a very, unfortunately, it's not a very meaningful question. You can make it what you want, depending on how you choose that scalar product.
There's something that's confusing me, is like usually in tight Muller space of a surface is just like some finite dimensional space.
Sure.
So how come it became infinite dimensional here?
Well, of course, right, I defined it to be like that. So because the surface has a boundary, I can choose what I do with the boundary. Maybe more famously, there are finite dimensional tight Miller spaces defined by Mirzakhani, and there you choose the geodesic boundary, and you do something with that. And here we choose the absolute boundary, and that's what happens, it seems, in the physics applications. They want to have, and I will tell you why a little bit. Maybe even like on those pieces of the board. Right, so yes, this is a kind of, there is a relation between those geodesic boundary and absolute boundary tight Miller spaces.
Yes, it's a standard practice. Is the action?
If you speak louder, maybe someone gonna hear you.
Is the action of this diffeomorphism group free space? Is the action of the diffeomorphism group free on the Teichmuller space or all in the space of all manifolds.
Right. Okay, I'll give a comment on that. Like, not always. We will now see, right? Okay, let me go directly there. Maybe one very prominent example, both on the physics side and on the math side, is as follows. Suppose I take sigma to be just a disk, right? A surface of genus 0. So in that case, the Teichmuller space of the disk, what can we say about it? On the one hand, let me just tell you, like, so it's isomorphic to diffeomorphisms of the circle. Now, without universal color, quotient by the Möbius group, PSL2R. So that may be an answer to your question. In that case, the action is clearly not free. Right, now this space is sitting inside so-called universal Teichmuller space that people study in complex analysis. So this is a sort of smooth part of it. And this is the Teichmuller space where you find surfaces of all genera. So some kind of weird construction. It's also equal to one of the coadjoint orbits of the Virasoro algebra. And that's actually the most studied orbit of the Virasoro algebra. Maybe we get back to it later on.
Sorry, this diff plus 0 of sigma bar, is it normal inside, is it a normal subgroup of?
So this guy.
Yeah.
Yeah, sure.
It's normal?
Yeah, of course. Yes.
I'm wondering, this Teichmuller space has an action of diff plus and not diff plus tilde, right? Or like
Which one?
the one
That
of the
one.
examples, yeah.
Yeah. I mean that.
Does that mean that the extension is trivial?
No.
Or-
No. No, but you know, tilde is okay. There is a difference between, like, you know, geometric symbols, tilde and hat. So hat is a hat is a central extension, and tilde is universal color.
Oh,
So these are two, like, different geometric phenomena. Right. So maybe one more thing to tell you how physicists think about it. We don't know how to interpret it, but who knows? It's also interesting. So physicists are thinking that actually in their theory, so it lives not quite on the surface. It lives on a smaller piece with a boundary, which is called the Wiggly boundary, which sort of, they think it oscillates near that infinity boundary. So that's what they say. We don't quite know how to interpret it. Probably, right, if we were smarter, probably I would have told you how to relate it, but I don't know. So, and what they're interested in, they're saying, well, there is this theory in the bulk, this theory that I described to you. And then they want to say that it's equivalent, or the physics word for equivalent is due, right? That's the translation. So that theory is due to some theory on the boundary, which is called the Schwarzian theory. Right? So that's the physics way of talking about it. And our current take at it, this duality is these two statements. So there is a Hamiltonian action, and there is a non-trivial central extension, and that central extension is Virasoro. So that's how we translate it for now for ourselves. Okay, so now I want to spend the remaining part of the talk by telling you a little bit about the proofs. And I think those proofs, as I say, that's not necessarily all boring. So there are some interesting or revealing moments about how it works.
Expected that this kind of quotient of type by Diff-Twiddle depends on genus. So, but isn't this kind of at odds with saying that the theories are dual? Or maybe they're dual for some like trivial geometry.
Let's postpone like the discussion of duality either to question session or to put a break afterwards or whatever, like to some future, right? Okay, so so there are like 3 or 4 steps, maybe 4 steps, one can say. And the first step is a sort of relatively standard move, how you pass from studying metrics to studying connections. And that you do using Cartan's moving frame theorem. So suppose I write my metric using some orthonormal coframe, alpha 1, alpha 2. So G is alpha 1 square plus alpha 2 square. Alpha 1 and alpha 2 are now 1/4, right? So then Cartan's moving frame theorem is telling us that there is a unique one form, sigma, which verifies Cartan's structure equation. I never know how to write the correct sign, but I know for sure that the signs in the 2 equations are opposite to each other. So then a very beautiful, I don't know, probably standard for you, but still quite surprising fact is that if you form the following 2x2 matrix with components being 1/4, so this is an SL to R connection if you wish, then this guy is flat. If and only if G is hyperbolic. So you can basically trade the hyperbolicity condition on your matrix to the flatness condition for that guy, right? That's a standard vanilla thing, but it doesn't make it less surprising.
Is it a 2-dimensional phenomenon or is it true in generality? You can recognize
that's a 2-dimensional thing. Yeah, I don't quite know. Maybe okay. I didn't look into how kind of what the probably. Yeah, of course, people trade, but maybe if anyone in the audience knows the more precise answer, that would be
What
well.
about degeneracy of G? Because I thought this is the subtlety, right? I mean, there are more flat connections than non-degenerate methods.
Sure, but here, I hope I formulate my statement carefully. I start with a metric which has which is a metric, and it has a orthonormal coframe. Then there is that sigma, it's unique, and now I write that thing. Right? I don't tell you that any flat connection corresponds to a hyperbolic metric. I say that I write such a flat connection, and if it's flat, such a connection, and if it turns out to be flat, then G is hyperbolic. And if G is hyperbolic, then this expression.
Let me rephrase the question. What does it mean, that connection? I mean, what's
I started with a Riemannian metric. I chose any orthonormal coframe.
No, but can you formulate this intrinsically? What's the form of this connection means? I mean,
what do you mean?
Typically, the main issue between relation gauge theory to gravity, it's exactly the non-degeneracy.
Sure. Yeah, I understand your question. You're saying that suppose I took some SL2R flat connection and try to compute alpha 1, alpha 2, and sigma, they're uniquely defined. Then in general, alpha 1, alpha 2 is not a coframe. You're right. But I don't state that, right?
Yes, right. Sometimes it's called the spin connection, if it's computed out of the group frame.
Yeah, I agree. In principle, there is a part of the proofs which is dealing with that, but I'm not gonna illuminate on that because that gets a little bit technical. Okay, so now so the step number 2 also starts in a relatively standard way. This is called the Jackiw-Teitelboim 2 form. And the Jackiw-Teitelboim 2 form is using the scalar product on SL2R. So you write a 2 form on the space of connections, or if you wish on the space of flat connections, that depends a little bit on your taste. And here, this delta is a Dirac differential on the space of connections, right? That's a 2 form, which is clearly closed. No doubt about that. If you look at it on the space of all connections, which is the sort of vector space or affine space, it's not difficult to convince oneself that it's non-degenerate. So that's basically back to our story. Here, our M may be a vector space or an affine space with a rather naive constant coefficient 2 form. Right. Now, there is still a sort of interesting observation. So now we want to put those guys into the formula. Now recall that the metrics, they diverge at 1 over y squared. This means that those connections A, which have alpha 1, alpha 2, sigma, like one can convince oneself that they actually diverge at 1 over y at the boundary. So a priori not completely clear whether this integral of a Jackiw-Teitelboim is well defined. And here 2 things happen. First of all, one should limit coframes to so-called adapted coframes at the boundary. Here I'm writing a dual frame. There is one direction which is canonical. This is direction along the boundary. Let's choose one of the vectors along the boundary. And in that case, so if coframes are adapted, then some miracle happens and this integral actually converges. So this is interesting. I don't quite know, right? Hyperbolic geometry has many miracles. And since I'm saying that, this means probably I don't understand it very well, right? Miracles is an unhealthy thing. However, it's still very pleasant that this integral, which normally here diverges at 1 over y squared, it turns out that it is simply convergent. And that expression does make sense. Now, what happens? Let's have a look. So our space of interest is a tight Müller space. And now, right, we are dealing with coframes. So instead of metrics, we said we have maybe adapted coframes, coframes adapted to the boundary. And now we want to divide it by that group of diffeomorphisms. And also, right now, there are some coframe rotations, right? Because for each metric, there are many coframes. So coframe rotations is something like maps from sigma to the rotation group. We can write it SO2, or we can write it as a circle. So that's roughly what it is. Maybe I should say that here there are also some global issues, but I choose to ignore them because in the end, they are relatively easily resolved. So for instance, you can ask me, that on the surface, typically there is no global coframe which satisfies those conditions for topological reasons. But, okay, let's ignore that. One can do this. Okay, so now maybe one can say we now have a two form, right, on that space of coframes, these two form, and it turns out that the action of all that group is Hamiltonian. So a priori, we are sort of in the framework, infinite dimensional analog of the framework that we had. But then we were discussing that one needs to do reduction, right? And the question is at what level and how does it work? So this action is Hamiltonian. And it turns out that the image of the corresponding moment map, or maybe first of all, I should say, the action is Hamiltonian and the cocycle is non-zero. So the action is Hamiltonian, the cocycle is non-zero, and the image of the moment map is always sitting in one single coadjoint orbit of that central extension. Remember, we had to choose the coadjoint orbit, choose the level, but here there is no choice. There is only one coadjoint orbit, which is always hit by that moment map, whatever it is. I can, if we have time, I can show you what the moment map is, but so for now, so reduction. We now represent the tight mirror space as coframes, points in that mysterious coadjoint orbit, subject to equation the moment map plus x equal to 0. Divided by this huge group. So this is a symplectic reduction, right? So that's why.
Is there some geometric meaning to the situation where the moment map hits exactly one coadjoint orbit?
Yeah. Let's get back to it. Yes, in principle, probably. Yes. Yeah. Yeah. I'll tell you a little bit more about it. Let me just do the last step, and then we go into the discussion where I tell you a bit more. So, right. Now we said that on this space, there is an action of diffeomorphisms of the boundary. Now it turns out that this action is also Hamiltonian. With C not equal to 0. And then, as we discussed already, this means that we have Virasoro. Now, maybe a little bit in the preview, I wanted to end up with open questions, but now this is one good point where I want to state an open question in that theory. You know, at the moment, you may be wondering, I'm not telling you much how comes that C is not equal to 0, right? I think in an ideal talk on that topic, I should have given you some really good reason, like kind of some topological reason, whatever, why C is not 0. But the problem is, I don't know what that reason is. I'm not telling you very much of how we get it, because we get it by a computation. We look at that action, compute its moment map, compute the corresponding C, and discover that it's non-zero. That's certainly a nice kind of in terms of experimental mathematics way, but it's not a very conceptual way to do it. So here are several thoughts why this might be the case. So one thought is that maybe that's because that guy was non-zero. So that guy is sort of maybe a bit easier to understand why that guy was not zero. We have a better arguments because it's inside gauge theory. In gauge theory, in principle, is clearer or better understood thing. So this one, maybe we can understand why it is non-zero. And one conjecture is that this guy is non-zero because that guy is non-zero. But it's not clear. One more idea, right? We start with the with this invariant pairing on SL2R. And there is all this story, especially now in derived geometry, right? We are told that a non-degenerate pairing on the Lie algebra, it corresponds to a shifted symplectic form on the space BG. And then there is the whole descent story, right? How that thing defines for you the Chern-Simon section, defines the Atiyah-Bott form, and eventually defines something like this non-vanishing central extension. Can we somehow trace a line to this guy? Okay, at least I don't know how to do it, but it's not excluded that some people in the audience might have ideas. It would be very desirable to have a conceptual understanding why this C is non-zero. Maybe to add one more thing to that. So if you just look at the gauge theory, right, at the theory of Atiyah-Bott forms on surfaces with boundary, there you can also ask how the diffeomorphisms of the boundary would act in a Hamiltonian way. And they actually act with trivial central extension. You know, here, maybe look at this thing. We started with a product of two spaces, and coframes, that was something like gauge fields. It turns out that your diffeomorphisms act on that guy in a Hamiltonian way, and on that guy in a Hamiltonian way. And here, C was actually zero. That was very confusing for me for a long time, because I knew that in gauge theory, C is zero, but then the physics paper was saying C is non-zero, like how comes? And it turns out that this C comes from that quadrant orbit. Right. Now, maybe the last thing I want to do, I want to show you the formula for the moment map. It's quite a fun formula, you will see, or complicated formula or confusing formula. And maybe I take this part, this rectangle, to write it down. So I write for you a formula, and then maybe I have a good story about the context for that formula. I apologize for those who already attended one of talks on a similar topic. That's always the same story. So the moment map for the action of diffeomorphisms, it's naturally a second order. You can arrange it into a second order differential operator on a circle. So such operators are called Hill operators. We'll come back to that in a second. And now I should tell you what is T of x, right? T of x should be a function of your hyperbolic metric. So let's consider again in local coordinates the lines of constant T. Maybe these are those Wigner boundaries, who knows? So they have a geodesic curvature, kg of which depends on x and on y. One more miracle of hyperbolic geometry is that if you subtract 1 and divide by y squared, this guy has a limit when y goes to 0. So it goes to some function. Now, the hyperbolic metric we can write it as something like this: a square, which is a function of x, dx square over y square, plus other terms. So I'm now trying to Laurent expand it in y, in the boundary defining coordinate. So then t of x turns out to be 1/2 a square ag plus 1/2 a double prime over a minus 3/2 a prime over a square. So this is an interesting, complicated, a bit mysterious formula, right? This thing, of course, reminds you of the Schwarzian derivative. That's how, like, physicists make connection to the so-called Schwarzian theory. There is one more term here, which depends on this geodesic limit of the geodesic curvature. And this gives you a little bit of a glance into whatever, how the real machinery. So that's one of the simpler formulas from the real story. Now the story, like in one of the talks about it, someone from the audience asked me Hill operators. Why Hill operators? What are Hill operators? Who was Hill? And to my shame, I didn't know the answer, but someone in the audience knew the answer. And now I also learned the answer, and I want to tell you. Sorry again, people, if you already heard that story. So Hill was an American mathematical physicist in the end of the 19th century. And he was studying the motion of the moon under the influence of the sun. And that's how he got those periodic operators. And I actually looked at his papers. So his first paper about it is published in Annals of Mathematics #1. If I'm not mistaken, pages 5 to 10. So this is actually the second paper published by Annals. And I actually looked at the paper. There is some whatever nonsense about the moon. The moon moves around the sun, very good. And then, but you come to page 10. You come to page 10. And then usually you see what? Like you expect conclusions and references. But actually nothing like that happens at page 10. Page 10 ends like to be continued. And then you go to the second issues of Annals. And you see again like the continuation of the paper by Hill, like the kind of the moon again moves and so on, right? And then, as you can already guess, in the end of the paper, it's again to be continued. So I think it ends in #3, something like that. But apparently that was the style. So you would get your whatever issue of a journal, you would read it like it's like a novel. You kind of read part of it, and then you don't go on the web to see the whole thing. You just wait for the next issue, right? So I think that's maybe a good point to stop, and then we should be also waiting for the next issue, right, of the conference. Hopefully, thanks again for the organizers.
Lots of things, Anton. Questions?
So what happens if you choose y differently? Will it be the
Yeah, of course. Yeah, that may be one thing. You can of course choose x and y, or especially y. You can choose y differently. Of course, that thing shouldn't change. You're going to have like a going to change, k going to change. Of course, that's and even you can choose x differently. Then we know that t should transform under the coadjoint action of the central extension, and that thing would also change. Yes, this kind of course, one of the claims is that the formula does make sense. It's equivariant under the diffeomorphism actions.
Will you reveal some of the secret why?
No, but no, okay. Like maybe it's maybe one thing which is not a secret. that seems to be automatic from, right, this story, or you mean geometrically, why, what is this guy geometrically?
Or whether there is a different way how to say it so that it becomes obvious this kind of claim.
Most probably.
Okay, thanks.
So this theory is essentially very similar to BF or Chern-Simons theory, right? For which we have a fairly good understanding of the reduction of the moduli space of flat connections.
Yeah.
So why is this a different story from that one? Like,
Okay, like okay, first of all, maybe again, the answer fully, I don't know, but maybe I can give you some indications. One indication is that what Maxim already mentioned, like this gravity is only part of gauge, right? They're not all flat connections
yes.
correspond to metrics, and maybe that's also I should say related to that. This group is not fully a gauge group. So this thing is a part of the gauge group. So this thing in some way, but okay, the group is different, and maybe the most important thing I believe that's this thing, right? You have some kind of weird controlled divergence of your connections at the boundary. And I would say, to me, that's the main candidate why it all goes somewhat differently. Maybe there is a more general story how you can do such thing.
Just practical question. Can you, when you write GT action in terms of A, is it actually BF theory or something?
Sure, and of course, it's in the bulk.
Okay.
In the bulk, it is BF theory, but among us, right, the most important things seem to be happening on the boundary, right? When I'm telling my theory how to behave near the boundary, so but yeah, it's BF with some boundary terms.
Those boundary terms, can you write in some nice way? I mean, in terms of A, flat connection, or sorry.
I must say, okay, certainly in the papers, you're going to find boundary terms written in all possible ways. We didn't try to study exactly how it corresponds to the picture that we studied. So, right, I gave you definitions. We believe those definitions correspond to what happens. At least otherwise, we don't believe there will be symplectic structure in the Virasor action, but that part we didn't make precise. Our starting definition is that definition of the Teichmüller space.
Sorry, just briefly. So if you don't take that particular boundary condition, just restrict metrics to the boundary, is there a problem or?
No, but it's going to be different a priori, right? I mean, you can, for instance, probably you can force maybe geodetic boundary, or you can force something else, right? Here, what happens, or at least the appearance of Virasora, that's almost for sure. Without doing that, this argument that the tier-bot form does not give you any central extension. You need to fight it in some, or whatever fight. If you want Virasora to be there in the end, this should not kill the whole program. And here, whatever, right? Because you get that exceptional quadrant board with all the central extension of that guy, that somehow it, yeah.
So that's an interesting modular space. I never thought of it, but so does it make sense on a pair of pants? And is it another way to think of Graham-Seagal's approach to conformal field theory?
Probably you can probably glue those things as well. But gluing, I must say, it would probably mean that when you glue to infinity, you cannot quite glue to infinity boundaries. You would have to cut them to geodetic boundaries and glue geodetic boundaries. I think that would amount to that, to be honest.
That relates to, actually, that question relates to another one. So there's a nice combinatorial construction of coordinates.
Yeah.
Teichmüller space. Universal Teichmüller space is also, there is a tendency extension. So in general, what do you expect to have at least an equal coordinate?
Yeah, okay, that's actually, maybe this gives me an opportunity just for 30 seconds to say that if the genus is at least one, we have explicit Darboux coordinates. It is interestingly and confusingly in the case of G0 0, which means the simplest space of a disk, Darboux coordinates are not known. But like last week, I got some preprints, so I don't know whether they are posted or not. People in probabilistic approach solving that theory for a disk. And one hope is that maybe if I or someone else reads those papers, maybe one can get a hint from probabilists how to deal with that problem. But probabilistically, there is a claim that they construct the parts integral with for that space corresponding to a disk.
I have a terminology question. So this interesting phenomena that you described, that this theory sort of seems to localize itself near the boundary, is that what physicists, which for physicists goes under the name holonomy, holography?
Yeah, sure. That would be whatever 2-to-1, whatever holography between two-dimensional and one-dimensional. So, yes, that's the right word. I don't know whether it helps.
So just to relate the subject of this talk to the previous talk, DF theory has a deformation which is Young-Mu. So what's about JT gravity? Can you do these deformations?
Oh, people, I think people were looking, in particular, our friend Thomas in his younger years, right? Thomas Strobel. So there was a whole big machinery constructed around PF type gravity series in a much more general setup. So it is all kinds of deformations. So I don't quite remember, but that time I think the focus was more on maybe Minkowski space. And they were trying to classify all solutions like Penrose diagrams, like building all kinds of interesting universes built for that kind of series. I think there was a whole series of papers with rather complete classification of those universes, but other than that, and for different types of deformed series.
But from modern point of view, from your story, is it?
Yeah, but you know, Minkowski is rather different from Euclidean, right? Euclidean gives you all those kind.
Why you suddenly talk about Minkowski? Let's do everything.
Sure. But as I say, like those perturbations, they were more like studied before for Minkowski setup because people wanted to use it as a toy model of realistic gravity, I think, or whatever. Learn something for the future study of gravity in our world.
Well, let's thank you. Okay.
I think many thanks, of course, should go to the organizers and to other speakers of this conference. Thank you.
In my mind, it's all the participants and the speakers who are energizing everybody. So thanks a lot.